Hello and welcome to another tutorial on composing with OpenMusic, computer-assisted composition software. This will be the first of maybe a couple of videos on methods of working with interval classes in OpenMusic. And specifically, we're going to look at making some patches that will calculate the interval classes of some pitch material that we work with. And again, this is something that I often find myself using in OpenMusic. It's a way of composing that I've found really useful recently. But even if you're not particularly interested in composing with interval classes or analyzing your pitch material for interval classes, this will be helpful to just demonstrate some features of working with OpenMusic. So specifically, we're going to be looking at different types of patches, how to use patches within patches. We're going to look at some more examples of various functions to perform on lists. So even if you're not interested in maybe the music theory behind this, it'll also be a practical demonstration of some really useful OpenMusic techniques. So let's get started. And to just begin with, this will be maybe some of the pitch material we'll work with. I've just dumped this in here, but for now it's not really all that necessary. So what we want to be able to do in OpenMusic is identify the intervals between various notes in a chord. So I'm going to be working off of a prototype that I built, and we'll kind of work through this patch step by step as we go. But maybe the first thing that I'll take a look at here is to analyze the structure of the data that's representing this series of pitches. So let's add an OM plus object. This is an addition object. And we'll connect that little patcher chord and evaluate. And you can see down here in the listener that we have a two-tiered list, right? So we've got one big list with the opening parentheses and the closing parentheses. And within that list, we've got 1, 2, 3, 4, 5, 6, 7 objects. And each of those is also a list, because it's surrounded by these parentheses. So one thing to know about the structure of pitch material in a chord sequence object like this one is the fact that it groups chord objects by these sublists. So let me show you what I mean by that. I'm going to use a special object called flat. And this will very literally flatten the two-tiered structure of this list that we've seen into just a one-tiered list. So it's gotten rid of all the parentheses surrounding each of these sub-lists. So now instead of having a list of 1, 2, 3, 4, 5, 6, 7 lists, we have a list of 7 numbers. And again, the only difference being that these up here were surrounded by parentheses, and down here they're just by themselves as elements of this list. Okay, so now what I'm going to do is I'm going to make another chord sequence object, and I'm going to see what this does to our material. So I've just evaluated, and we'll see that there's really no change, right? This is laid out the same way in both of these chord sequence objects, where the pitches are just a series of pitches. So the way that I can actually change the layout and group all of these into one chord will be by using a list object. So we've made several lists just by double-clicking, using parentheses, typing in some data, right? And that makes a list. But this list object is a function in OpenMusic that is specifically designed to create lists. And so you may be wondering, well, why do we need a whole other function to create a list when we can just double click and make one ourselves? And the answer to that is one of the really amazing features of OpenMusic is its ability to automate processes and to recursively apply functions to the data that you're working with. So, for example, I haven't spent a whole lot of time programming with Lisp, but one of the amazing features about the language is that a Lisp function can be represented in a list, just like Lisp data can be. Data and functions take very much the same format, which means that you're able to write some data in the language, telling the language how to interpret data, which is kind of crazy. It's a very powerful language, and that's sort of the principle behind this. So what we're going to do, you'll notice that this list function only has one outlet, and that's not particularly helpful. We can't really do anything with that. So if we click on it, hit evaluate, we just get nil. Right, so that's really no good. What we're going to want to do, and again, I work on a Mac, and I would have to look up the keyboard shortcuts for Windows if you're on a PC. But what we want to do is we want to hit Alt and then the period key. Really, it's Alt and the greater than symbol. So if you're on a Mac, you're going to hold down Alt Option as well as Shift, and then you're going to hit the greater than symbol on your keyboard. Oops, I'm sorry, I misspoke. You're going to hit Control Shift and then the greater than symbol on your keyboard. My apologies. So you'll notice if you hold down Control Shift and you type the greater than, it's going to add inlets. And if you type the less than symbol, it's going to take them away. So this is really useful, and like, for example, one of the things that we can do with list is we can make a list of lists. So I just made my own list. I'm going to click on that, hold down Control. Oops, no, I am going to hold down Alt Option and drag, and duplicate those really quickly. I'm going to connect these little patch cables up and evaluate, and all of a sudden I've got a list of lists. There, we can see it being repeated 3 times. So that's what we're going to do. We're going to do that here. We're going to type in list, Control Shift, right key, the greater than symbol, and then connect it up. And before we see it here, let's evaluate this list, and we can see we've got now a doubly nested list, right? So we've got the outer layer parentheses for the first level of the list, and then the second one. And what that's going to do is, instead of treating each of these as individual pitches, it's going to treat them as components of a chord. So this list now represents one chord with 7 pitches. And when we evaluate, we'll see that OpenMusic has now grouped those together into a chord. And that's the reason this object is called a chord sequence, because it's intended to represent a progression of chords. So you could add further chords in between, so to speak, these 2 parentheses, and get a chord progression. Great, so we've got our pitch material, we've got a cool chord here that we want to analyze to discover the interval class content. And again, you may be saying, well, you can just look at it and figure out what the intervals are, and that's certainly the case. But the thing that makes OpenMusic so powerful is that you can have the software do that for you, and do it on a really large scale. So you can work with a large collection of possible sonorities to use in a composition, and do some analysis and figure out ones maybe that you really want to use. Okay, so what we're going to do now is we're going to add a new patch. And if you've seen some earlier videos, you know that you can go up to File, New Patch here, and it will just add it over on the side. And that's certainly very useful. Another really quick way, you can use the keyboard shortcut Command 1. Oops, maybe not. Oh, I guess you have to be, okay, you have to be in the workspace. Type Command 1 and you get a new patch. Another thing that you can do is you can right-click anywhere in the patch, and you can add a patch that will be stored inside this patch here. So you'll notice that this patch doesn't appear in the workspace. It's not a patch that can be accessed by any other patch in the workspace. It's unique to this patch and it's being stored here. So maybe one difference that I'll point out, let's say we make a list in our patch and we click, hold down Alt Option and drag and make a duplicate. And as we would expect, we've got the same list. But if I change the list in this second patch, it doesn't change it in the first, right? So this is keeping these two instances of this patch separated so that one doesn't affect the other, which is very useful. However, if we were to make a new patch here in the workspace and drag 2 copies into our patch, and if we were to make a list in one of them, you'll notice that the same thing happens in the other. And in fact, it's not even going to pull up 2 windows because it treats these 2 instances of the patch as one and the same thing. So that's a good thing to know. I think of these kind of teal, weird green ones as like the global sort of patches, and these internal patches as ones that are just specific to the patch in which it is contained, this OpenMusic tutorial patch. One last thing to note is you can convert one type to the other. So I can take this, drag it over here, and all of a sudden it changes color, and it's now a global patch. Yes, we'll erase that. And yes, we'll erase that. And we'll get rid of those little skulls. By the same token, you can drag a patch into a subpatch here. And if you select it and type A for abstraction, I assume, it will turn into a local patch, just like if you had made it an internal patch here. So if I change this patch, oops, let's drag and open. There. So if I change this patch here, it won't have any effect on the global patch stored there. So let's start by making a true global patch that we'll use, and let's name it chord tone interval list, because we want to come up with a list of intervals of these successive chord tones. All right, so let's go ahead. We'll open this up. And as I'm sure you've noticed, there are various buttons up here in the top left, and these are for inlets and outlets. So you can add as many inlets, as many outlets as you want, and OpenMusic will automatically update the patch representation. So that, for example, if I wanted to bring the pitch data from this chord sequence into the patch, I could connect it to that inlet and be able to access it from this patch here. Now you'll notice, so for example, if I make another chord sequence, connect that inlet, preview it, and evaluate, you'll notice that when I evaluate, it doesn't actually show me this data, right? So the chord is kind of the patch is kind of abstracted away from its specific instance right here, and so it's not going to feed the data into this like template of the patch. But say I want to do some debugging and actually figure out what's going on. One thing that I can do would be to maybe make an OM plus, an addition object, evaluate that. I get the results here in the listener. I can copy those, and I can double click this input, and it'll open up a little menu window where we have an option of setting a default value, and I can right click, paste, and apply and close, and now by default the data that I just pasted will be the default output of this inlet into this patch. So that's a handy way if you're working in a patch, need to do some debugging and figure out, why isn't this working on the outside when I go in here. That's a handy way to do that. Alrighty, so now what we're going to do, we're going to add a new type of object that we haven't looked at yet before, and this is an OM loop. So if you've done any work with, with some coding or programming in the past, you're probably aware that loops are a really critical part of accomplishing what you want to do. So loops are for working through data in a sort of iterative way, where you want to maybe apply some sort of function or process to a large amount of data. So we've made this loop, and let's go ahead and open it up. And we'll see that this sort of window is really different from other ones because the loop object is so special. So we've got some various things, and if you're interested in what they all mean, you can certainly go and look at the documentation. For now, we're just going to focus on a couple little things here. So what we're going to do, let's go ahead and start by making an object called length. And what length does is it's going to show you how long your list is. So I still have that data from the listener down here pasted on my clipboard. So I'm going to double click, paste, and connect to length, and we can see in the listener it's going to show us that this list is one item long. And you're saying, wait, there are seven numbers in there. Well, remember, this is a nested list. So if I use flat to flatten out this list again, and then connect it to length, then we'll see a single tiered list of 7 objects. And sure enough, that's what OpenMusic tells us down here. Great, so this length object will show us how long our list is, and we'll connect that up. And now what I want to do is make a subtraction object and subtract 1. And the reason we're going to do that is because we're going to iterate through this list of pitches in our chord, and we're going to do that by looking at the index for each item. If you've seen the last video, you remember that the index is the number that tells OpenMusic where in the list a particular object is. So we're going to connect this length minus 1 to the right inlet of this for loop. So this for loop is going to spit out numbers starting at 0 and going to this upper limit that we've set of the length minus 1. And again, we're doing minus 1 because list indexes are counted starting at 0. Great, so we've got that for loop. And now what we want to do is we want to ask OpenMusic to calculate the difference between successive pitches in our chord sequence. And so the way that we're going to do that is by adding some nth objects and then a subtraction object, OM minus. And so what these nth objects are going to do, they're the way that we can translate back from an index to the actual object in the list that the index represents. And so what we want to do here, let me check my template real quick to just double check how I did this. Okay, so we're gonna connect the outlet of the for loop to this first nth object on the left inlet. And then we're going to take this, this input object and connect it to the left inlet here. So what that's going to do is, as this is ticking through 0, 1, 2, 3, 4, 5, 6, it's going to say get the 0th object from our list, then the first, then the second, then the third, and so on. The other thing that we're going to do then is we're going to make a plus object, OM plus, and we're going to take the constant output of this for loop and add 1. So if this picks the 0th object of our list, this nth will pick the first object of our list. So we're going to connect that to the left inlet, take from the input over to the right inlet here, and now we've got our for loop counting through the indices of the list, where this left one is the first, and this right one is this immediately successive object. So now we can actually go ahead and subtract them. But one problem that we'll run into here if we just leave it like this is we can end up with negative values in terms of MIDI sense, which isn't going to be super helpful for determining the distance between successive pitches. So what we want to do is make a new object for absolute value. The absolute value, if a number is negative, it'll get rid of that negative symbol in front of it and just leave it as a positive integer. Great, so at this point you might want to check and see what's going on, and if you do that you're going to run into a problem. So if I select this absolute value object and hit V, it's going to tell me you can't evaluate this box. What are you thinking? And the reason why it does that is because OpenMusic at this point isn't going to let you iterate through that for loop while you're editing this OM loop object. It doesn't like that. So for the moment, we'll just take it on faith that this is going to work. But there's one other problem that we could possibly run into, and that would be a case where, say, the difference between our two successive. Oh no, I'm sorry. Let's see. Oh yeah. So the other thing that could be problematic here is running into the end of the list. So so this for loop begins counting at 0. It's going to go all the way up to 6. But this addition is going to ask at some point for the 7th index of this list, and we know that's not going to work because the indexes start at 0 and go up to 6. So we need to make a way of handling that so that we don't bump into that problem. So let's just do a quick demonstration to see what would happen if we didn't handle that properly. So I'm going to make this collect object, and I do that by clicking up here and pulling this down here. I'm going to connect to this inlet, and what this is going to do is this is going to ask this OM loop to keep track of the results each time it works through the loop, so starting at 0, then 1, then 2, and then at the very end it's going to output them all with finally. And if you want more information, you can highlight that, type D, and look at the documentation. Okay, so we've got this loop. We're going to go ahead and select it and evaluate, and sure enough, we get a problem. We get an error message. And the reason for that, again, is because we can't take the absolute value of nil. And the reason we're getting nil is because we've asked OpenMusic to take that index number 7 of this list, which is a list object that doesn't exist. So what we can do to fix this problem is we're going to use, let's see, this object. OM equals. Okay, so this is there. OpenMusic has some slightly different variations for determining if objects are equal. So for example, one that you can use is just the native Lisp equal function. In this case, we're using OM equal, which is slightly different. And again, I'd have to go back and check the documentation for the differences between those. But what we're going to do is we're going to take the outlet of this length object and connect it there to one of the inlets of this equal object. And then what we're going to do is we're going to take the result of this addition object here and pull it there. So what we're asking OpenMusic to do is determine by the time this counts up to 6. So we've counted up to 6. This plus gives us 7, and we're asking OpenMusic to determine if this 7 is equal to the length of the list, which it will be by the time we've counted up to 7. So what it's going to do then, it's going to return a value t. So just to demonstrate, if we do this, and if we do this, and this, so we're asking OpenMusic, is 0 equal to 0? And in the listener it says T for true. So if you know a little bit about logic or Boolean algebra, you know that sometimes truth and falsity can be represented by 1 or 0. So you know that's part of the magic of binary, is that it's a way of encoding truth statements about whether something is or is not the case. So in OpenMusic, if something is true, if it is the case, it'll always be represented by T. And if something is not true, it'll be represented by nil. I think I mentioned earlier that nil is a really important part of the language. So this is going to determine if we've bumped into our upper limit for the indexes, the indices of this list. And then we need a way of determining what to do if that is the case. So we're going to make this OM if. So I'm going to connect this to the first inlet marked as test. So the way I think about this is this OM if is asking if something is true or false. And if it's true, it's going to evaluate whatever I plug into this second inlet. And that's all well and good, but we also need it to do something if this is not true. So as it is right now, this is only going to do something if this is true, if this equals function returns true. So to get it to do something else, we're going to hit Control-Shift and then the greater than sign, and it'll add this last inlet for an else case. So if this is true, we want it to return nil. And if it is false, so if we haven't bumped into our limit yet for the indices of the list, then we want it to return whatever absolute value we get from subtracting these two items. And that's the value that we're actually going to plug into this collect object. Okay, so now we can close that, save that, evaluate, and what do we get? We get nil. And why are we getting that? Well, let's take a look and see. One of the things right off the bat that I think might be a problem could just be the formatting of our input data. So let's take a look and see again what we've got going on here. If we just connect this up, we'll remember that this is situated as a chord, and so as OpenMusic is going through this for loop, it's only finding one object to work with. So what we need to do before we can evaluate this is flatten this list so that OpenMusic knows to iterate through the individual chord tones rather than iterate from one chord to the next chord object. So now that we've made that change, we can highlight and evaluate, and wonderful, we've got this great list here. And sure enough, that's actually accurately representing the distance. Here, let's open up here. Representing the distance in terms of cents between each of these chord tones. Now you'll notice one last problem. We've got this nil here appended to the end of our list, and the reason for that was our little failsafe that we programmed in right here. So one way that we can get around that is by asking OpenMusic to remove any, remove any specified object from our list. So I'm going to take that inlet to the right inlet here, and it's already programmed to remove nil, which is great. So I'm going to collect there, set that up, and reevaluate, and now our nil is gone. So we're left with only interval data, which is super helpful. Okay, so I think that's where I'll stop for now. We're on the first little leg of the journey in producing basically an interval class calculator for this chord. So in the next couple videos, what we'll have to do is look at converting our data to pitch classes, and then figuring out how to do some modular arithmetic to make sure that those pitch classes are limited to the 6 interval classes that we work with. So we'll see more of that, and that'll make sense down the road. But for now, thanks again for watching this video. I hope it was helpful. If you have questions, comments, or requests, be sure to comment below, and I'll look forward to seeing you next time.